All right, last speaker of the day, and certainly a friend of CSU and of mine. And I'm happy to have him back to give us some lessons on isomorphism problems that relate to tensors and perhaps some of the terrain nearby.
Thanks, James. Thank you, Christopher. And thank you, Alina.
I should have said your name is Josh Maglione, professor at Galway.
They should
have given some details.
That's fine. No. Detail. It's been this is hour 6, so
yes.
You know. But nevertheless, I thank the organizers for organizing such a conference and a workshop, and in particular James for the local organizer taking up that duty. It's a significant duty undertaking, is what I can say. And so I'm very much looking forward to going back to Pingree. I'm very happy to be in Fort Collins this week. It's just great. It's fantastic to be back. Right. So I was appointed the title "Comparing Tensors," which I thought was fantastic. So I love this title. It's a great title. But it was not my choice. So it was appointed from on high. And to continue the metaphor, we heard earlier that if it's sinful to choose bases, you know, maybe a subtitle of this talk is atonement. So we're going to be talking about isomorphism problems, and in particular, the many isomorphism problems. Okay. Right. So I actually want to come back to comparing tensors. How do we compare tensors? Well, actually I'll write that too. How to compare. And that's perhaps the little section title that I want to start with. So, I mean, you could think about it very strictly in the sense that we only compare tensors by looking at multi-way arrays, and two tensors are equal, equivalent, whatever, if they have exactly the same data. As in, the entries of that multi-way array are exactly the same. So that's a very strict way of looking at the world and multi-way arrays. But of course, what we want is something weaker. Yoming has already talked about this. Pete also talked about this as well. We want something weaker than strict equality. If at any point you can't read my writing, if it gets too small or too illegible, you just ask. You interrupt me, it's fine. I don't need to cover everything that I've written down in my little notes, so it's not a big deal. I'm around, so if you have questions, you can also ask me afterwards. Okay. We want something weaker. It should be comparable to something like isomorphism in algebra, or homotopy equivalence in tensors in tensor space, in topological spaces. This is something weaker than just a strict equality, okay? And we will look at the many or some notions. At the end of the day, we're going to have to choose something, and we're going to choose exactly what Yaming talked about. So this is great. You've already actually seen this. So the benefit of being the last speaker of the day is that you've already seen everything more or less that I want to cover. So this is great. I want to talk about notation. Okay. I like to actually work with multilinear maps. So I like to work with multilinear maps. We saw how to get various things from them, but let me actually take a little step back and say a little bit about what I mean by multilinear maps. So throughout, I'm going to say K is a field. Okay. If you'd like, you could actually think of this a little more generally than just fields, but I just want to keep it as a field. Okay. And what I want is I'm going to actually work with a bilinear map in the moment, just to write some things down. So let T be a bilinear. I'll use the same notation that Pete used, U, V, and W. These will be vector spaces, U, V, and W, K vector spaces, finite dimensional. Okay, and it's bilinear. Of course, linear in one coordinate is bilinear if for all little u in U. Actually, let's do it this way. prime for all v prime v, and I need something lambda k, right? You get your usual linearity condition, namely u plus lambda e prime comma v is going to decompose the sum and then, of course, in the other coordinate as well, okay? And that I won't write. Wait a second. Well, let's write it. Let's write it. uv plus lambda times t u. Okay? And I'll say this is linear in the first coordinate, linear in the second coordinate. Okay, so it's bilinear if it's linear in both coordinates. Multilinear, so we'll upgrade to multilinear. Okay, and I'll give you some notation now, what I usually just default to. So T multilinear map. I'll pick V1, VL, V0. Okay, those are all vector spaces. And it's multilinear if it's linear in each of these L coordinates, or axes, as James has mentioned before. Okay, the valence of this multilinear map, if you like, is L plus 1. We've got that 0 out there. And something that I haven't quite explained, this symbol I use to describe multilinear. So I won't usually write multilinear. It will be subsumed in that symbol there. Okay. So multilinear if linear in each coordinate. Okay. I like to work with multilinear maps, but I'm often given data that isn't exactly a multilinear map. Okay. For example, multi-way arrays. Those are not themselves multilinear maps. Of course, they induce multilinear maps, and I won't go too much into that. But to make this act of inducing a multilinear map explicit, I'm going to have what is known as some notation for interpretation. So we'll be explicit with the notion of interpretation. I believe James talked about this earlier. That is, this is simply just a way to interpret data multilinearly. Okay? And I'm going to use Bra-Ket notation, which I think James was also using this morning as well. And I wasn't asleep for any talks, but nevertheless. Do this with Bra-Ket notation. Okay, so let me rewrite these two equations here in a different style. Okay, and just so happened to be right at the same level. That was a coincidence. I'll use something like that, so T, and I'll put the same thing here. I'll just write maybe the first line. Second line will be overkill. Prime there. Okay. So what I'm doing is that this Bra-Ket notation, this object right here, so to speak, it's taking the data that is in here. In this case, it just happens to also be a bilinear map, but later on it can be multi-way arrays and these sorts of things, and it's interpreting that as a multilinear map. In this case, bilinear for that particular example. Okay, and this may seem very like, why are we going through all of this stuff? Well, I'm going to be dealing with multi-way arrays and matrices of linear forms and these sorts of things, and I want at the end of the day to talk about multilinearity, which is sort of a topic that James was talking about earlier with the notion of contractions as well. And I want to do it somewhat explicitly. Later, as in next lecture, we'll upgrade this notation to bring in what James also mentioned. It gives you a little bit of freedom to kind of play around with the indices. Okay? But we won't focus too much on that. Okay? So I think that's all I want to say about notation. And I'll stop here real quick if there are questions. Okay. Great. So now I want to look at some examples. Okay, some examples. So I want to look at 3 in particular, and I want to look at different areas of mathematics. First will be algebra. So we'll look at an example from algebra. We've already seen many. We've seen, by examples, I mean tensors arising, but not only just tensors arising. I actually want to think of it in terms of isomorphism, or whatever that might mean in different contexts. Okay? So from algebra, I need my notes for this one. Correct numbers, I don't want to screw things up. So, consider two-dimensional. I'll throw the word in non-associative. Not necessarily associative. In this case, it just isn't associative. Actually, I take that back. I didn't check. I won't claim anything. K algebra A, generated by 2 elements, x and y, might have a multiplication table, as we've seen a number of times today. Okay, might fill it in like this, and let me tell you how I want to fill it in. 2x minus y, x plus 3y, 2y minus x. Okay, so you might have some algebra that has that as its multiplication table, right? 2-dimensional so that I don't have to write so much. Could be more. Okay, and I've actually written a matrix of linear forms. So there's my matrix of linear forms. I might call this, what do I call this? I don't want to call it M, and that's going to be something else later. I won't call it anything. There's my matrix of linear forms. But I could also write down a grid of numbers, a 2 by 2 by 2 grid of numbers. And to visualize that, we'll go this way. All right? So I'm not going to throw the numbers in, but it's a little cube. And I'll draw my cube. You know, speakers seem to be required to draw the cubes, so there's my version of it. We're looking at a 2 by 2 by 2 thing here. And I'm going to split it up. I'm going to look at a particular slice. And I want to look at 2, 0, 1, minus 1, 0, minus 1, 3, 2. Okay, so this is in some sense the x. This is in some sense the y. And you can think of this as, well, it's so symmetric, this thing, you can put it in however you like and do what you want. Okay? Right. So that's a K algebra. And you might say, great, that's good. We can get a tensor from this, which is nothing more than the multiplication in the algebra. Let me give a name to this. M, multi-way array. Okay? And now I want to just actually go and describe what the multilinear map is, just the first time. This is nothing more than the multiplication in A. Okay? So it's just going to take a little u and v instead of k squared, map it to, using these things right here, u transpose 2, 1, minus 1, v, comma, u transpose 0, minus 1, 3, 2, v, and close it off. Okay? So here's, I don't think this is made explicit. It's maybe obvious, but here's an example. How you get from a multi-way array to a multilinear map. Okay? By the way, I noticed this in Pete's talk. He was doing things on the right-hand side. I'm doing things on the left-hand side. Okay? Just a note. Right. So back to tensor isomorphism. How does this arise? Well, I just chose some generating set x and y. I could choose a different generating set. Okay? Let me give some names to those. X prime is x plus y, and the old generating set y prime is 2x plus y in the old generating set. And now I have a different multiplication table. If I didn't tell you the secret sauce, you'd have to think about it for some time. I don't know if you can just stare at it. I'm not one of those that can just stare at it and figure it out, but here's the multiplication table. I'm going to cram a little bit, sorry. There we are. Okay? Of course, I just told you I chose a different generating set. So we know that the algebra that has this multiplication table and the algebra that has this multiplication table should be isomorphic. And indeed, that's the case. Let me call the associated multi-way array. I'm not going to write it all out again, but I'll call it n. I have m over there and I have n over here for this one. Okay. And okay, let me just say, let B be the algebra from n. I said it didn't work. Let B be that algebra from n. It's like 1 o'clock for me and my biological clock, so those will happen, I'm sure, a few more times. Okay, so of course there we know A is isomorphic to B. Yeah, and what exhibits that? A matrix X. Minus 1, 2, 1, minus 1. Okay, sort of the inverse of that on the columns there. Okay. And what does that actually mean? Well, it actually means, in terms of the multilinear maps, if I look at n, I've got some matrix X acting on the left of these two entries, U and V or anything, runs over all of them in k squared, is nothing more than this. Yeah, that's what I mean by an isomorphism of algebras. This is what it happens to mean on the level of tensors. Okay? I call this an isomorphism of tensors. Okay? Good so far? Great. Another example I want to do comes from geometry. And I'm going to go a little bit quicker now with these examples. Okay?
Just a quick question.
Yeah.
Are these algebras associative or anything, or they're just something?
They're non-associative algebras. I am not assuming any associative. Yeah. So I'm not assuming unitals or anything like this. Units or anything. Right. So, in geometry, I don't think I've seen this yet. Sorry, someone said something.
I think all two-dimensional algebras are associative. Right?
Oh, okay. Well, that's just
But not obviously. Not,
curse
that's what
of small numbers for
yeah, curse
right.
of small numbers, right.
But I mean, you scale this up larger dimensions, and then I'm not assuming anything. But I wasn't assuming associativity. James it just was appointed to me that these things were associative.
I may be wrong.
No, it's fine. It doesn't matter. Good. From geometry, I don't think this has been mentioned yet, but here we are. So we've got variables. Let's let x1, xd be variables. Okay. In a polynomial f, in this polynomial ring. And for now, I'm just going to write this as x kx there. Okay. Has a linear determinantal representation if there exist matrices, I'll call them A1 through AD, what do I use? Let's use N. K, such that F is the determinant of the following sum. Okay, so this set of this collection of matrices A is what's known as, to some people, a linear determinantal representation of the polynomial f. Okay, some people care about these sorts of things. Understanding which polynomials f have linear representations is a sort of key question in this corner of algebraic geometry. So I'll mention that. I'll abbreviate that to LDRs. All right, so that's one particular question that is pretty important. And what they do is, from my understanding, I'm not an expert in this at all, but I've been playing around with these linear determinantal representations. They start asking questions about, well, okay, I want to understand some specific properties of f. Maybe I can see that in the linear determinantal representations. Okay? And I don't see this as anything else but a tensor. Okay? Let me call this A. Right, these are matrices. These are slices. So A is now my multi-way array. It would be a n by d. Okay, and this would be the first slice right here would be the A1, and so on and so forth. Okay. Oh, and I should say, seemingly this is also connected, these linear determinantal representations are also connected to areas of linear and convex optimization and control theory. I say that with no authority, as just I've read papers that have connected these.
Do you have no restriction on n? Are we allowing n to be arbitrarily large in your question?
I would say so. Yeah. Yeah. And yeah, actually, I'll just leave it at that. Yeah, I would say so. There's no restriction there. Okay. Of course, if A is a multi-way array, then my tensor A would be of this form, namely k the n, k the n, k the d. Okay. And of course, we can change bases. We can change these matrices around, right? So not only is this a particular question in this field, but then there's also questions of classification. Can we classify those LDRs that arise? I'm not putting enough there to make it a proper question, but by classify, we want to classify up to choices of bases. Okay? That's basically the idea. And if we had something like the following, so let x, y be in GL and K, a general linear group looking at invertible matrices, then I could act on the left and the right, x and y respectively, on these a sub i's, and not really change the determinant in any meaningful way. Okay, and I can stipulate that the product is that, and I just will just for convenience, and then I can write something like this. Something like that. Okay, so one might consider classifying these LDRs for a particular polynomial or class of polynomials up to an equivalence that is something like this. You might not actually use this condition here. Or you might care about matrices that are symmetric, in which case you'd actually only use an x, and you would act by x transpose x to preserve that symmetric property. Okay, if I just called these, let me just write B here, even though I don't mean B is the sum, I mean B is really, I'll write it that way. B1, this is BD, and then B is my multi-way array. For this tensor here, we would basically be saying the tensor B is nothing more than A, X, U, Y, V. For all U, V, and K, right? That's what we would have. So in this context, we might say something along the lines that isomorphism, equivalence, whatever you like, is actually this equation right here. Not this equation. I care about this equation, maybe. That's fine. But in particular, they're not exactly the same. Third example and perhaps the shortest, just because I kind of want to keep moving, comes from QIT, quantum information theory. And there, let me also note, I'm oversimplifying things, but this is also, well, no, I'm just oversimplifying things. A system of n entangled particles, quantum particles, can be represented as a tensor, the following form. Let me just make sure. I think I want it 2C. Yeah, that's right. So system, or like this, squared. Now then I'll explain a little bit. Oops. I have here, of course, n copies. Okay, so what's happening here is the spin up and spin down are being recorded by a two-dimensional complex vector space there. Okay, and then this lives in some superposition, so a superposition is viewed as a linear combination of the two basis vectors up and down, say. That's why we're looking at a two-dimensional space. And then we have n entangled particles, so we have n copies of these c squareds mapping to c. Okay? So this is one way to represent an n entangled system, or a system of n entangled particles. Okay? One of the questions one might ask is, when are two systems of n entangled particles equivalent? I'll write that equivalent here. Let me explain what that might mean, what that would mean in my context right here. And that's what is known as, this is in particular called Sluck equivalence, which stands for stochastic local operations in classical communication, which is not something I carry around, but I sort of have my notes here. Nevertheless, what does it mean for me? It means the following. It means there exist matrices x1 to xn in SL2C such that, I have another system here somewhere. Let me write another system as T. Same setup, n copies of C squared here. Such that S of U1, Un, is nothing more than T of x1, U1, xn, Un. Okay? And you might call this your favorite equivalence, your favorite isomorphism. Or you might call this equation your isomorphism, or you might call this, or you might call none of those on the board. The point is, there really is kind of a lot of different notions of what it means to be equivalent, or what it means for tensors to be isomorphic. Okay, so that's the end of my three examples. The general landscape. There's choices. There's context. And what do I mean by context? There's a category. I won't go into categories and stuff, but I'll just sort of mention, kind of unite this all together. Okay, so you might have one tensor, V up to VL, V0. You might have another tensor. Let me just get away with identifying the spaces as exactly equal. Depending on the context, you might draw a different diagram. I'll draw one diagram that Ming's already mentioned, but isomorphism could mean Ooh, this is green. I thought the top is blue, but excellent. Okay, you might have isomorphisms. You use alpha and different isomorphisms. You might even have another isomorphism out here too, alpha naught. Right. You might call this tensor isomorphism, and this is actually going to be the one that we choose. So definition: tensors S T V1 VL V0 are isomorphic if there exist isomorphisms alpha I VI to VI such that the following equation holds. Let me get it right. I always screw the order up. I thought about this correctly at one point. I don't want to think about order of who's on first. So this is nothing more than this.
Can you put S and T on the above picture?
Oh yeah, sorry. Yeah, that would be helpful, wouldn't it? Yeah, S should be up here, T down there, I believe. These things map into, so I got that right. So that is one notion of isomorphic, and of course you can play around with this. We've seen examples where, in particular the one on the board, doesn't have something acting on this outside right here at all. You might change the down arrow, be something like an equality, so to speak. Let me use a different orange here. You might do something like this. Well, this is my way of saying I'm not doing anything. I'm actually leaving it constant. I'm not acting on that side. Oh, actually, both those equations have that condition. This one too. Yeah, and what one can do is one can not only choose down arrows, but one can actually choose up arrows and these sorts of things. So you have, in some sense, three possibilities, either a down, an up, or an equal sign. And then in a first example, where we're looking at algebras, we're actually treating all the coordinates as the same. So we have something like a partition of these axes here, where we can think of them as being the same and treat them in the same way and operate on them in the same way. Okay? I don't want to get into it further, but all that to say, there's a ton of choices out there for different categories. And this is, in some reason, why we see several different notions of equivalence, tensor equivalence. Okay. I want to simplify the notation here. Actually, up here. A alpha, the alpha naught inverse. And then I'll write it like this. How do I do this? Yes, dot there. That way I don't have to write all of these. Okay. So something like that. So this equation is just an abbreviation of this right there. Okay. Since they're isomorphisms, hopefully no one will be upset that I've taken an inverse. Questions? Okay. Now I want to talk about just state the problem. What's the problem now? Well, if you're thinking about this thing computationally, what exactly do I mean now? What's the data that's being given? I'm talking about multilinear maps. What are you giving to a computer, say? Let me make a problem statement here, so we can talk about. I'm going to throw k into the statement. I don't really think that's necessary, but I kind of like it. Okay, so the k tensor isomorphism problem. What's the input? I'm going to want multi-way arrays. I find these to be convenient to work with, easy to understand. 2 k multi-way arrays, A and B, and the output will be, true, false, yes, no, that's sort of a question. True if and only if. I'll write it like this. True, yes, or whatever you like for an output. True if and only if. this holds. And by this symbol, I'm just going to default to this one. I'm just going to assume we're in this category, except when we're not. But that's sort of the context here behind this. Okay. So in some sense, that's actually part of the statement in this particular problem, that category. Okay. One of the key questions that drives a lot of computational work is the following: does there exist an efficient, do I want to say that? No, I want to say algorithm. There we are. An algorithm that solves K tensor isomorphism, and now I'm just going to abbreviate it to KTI there, in time, a polynomial in the size of the input and yeah, I'll just leave it at that. So what is the size of the input? Well, okay, that certainly depends on the size of these arrays, but these arrays have some volume to them, and then for each entry there, I've got some entry in my field, element in my field. Okay, so it'll depend on the, let me use the word size of the array, the multi-way array. Right, so that is, let's use James's words. Valence, so it incorporates the valence, then it incorporates the various dimensions. Okay. So size is just my vague way of saying that function. Okay. So this would be amazing if this were true. I want to mention a reference by Joshua Grochow, Yuming Chow. It's called the Complexity of Isomorphism Problem for Tensors, Groups, and Polynomials 1. I won't say the subtitle, but it's from 2023. Say just this. And they have a fantastic figure there that connects tensor isomorphism to lots of other problems in computer science. And in particular, I believe group and graph isomorphism are there too. Okay? Questions? No? Okay. Time's doing good. So let's think just a little bit about this problem. If K is finite, then we have something like a brute force. We have what is called a brute force or an exhaustive search, because at the end, you're totally exhausted if you do get to the end. Brute force search. And that could be fun to think about for a bit, and you probably already have thought about it and know exactly what one would think about, but what are you exactly searching through? What are you looking for? I've got vector spaces here. I want to find alphas. Right, and I want isomorphisms between vector spaces. We know those to be invertible matrices. So we would search through the following group, say, GL V0, all the way up to GL VL. Yeah. This is some huge group. I don't need to tell you that, but you could just search through this whole thing, and if you don't find a single isomorphism, that is, you don't find this diagram, or I should say, this equation holds, then you just report false. If nothing found, report false. Otherwise, keep searching. Okay. So that's what we can do when K is finite. When K is infinite, well, you could generate matrices, I guess, if you'd like. That's probably not the approach you want to take. You can actually set up a polynomial system. A system of polynomials that you want to solve. System of polynomials over K. And as an exercise, that can be somewhat enlightening. Keep it small. but someone might try setting up that system of polynomial equations. How many polynomials do you get? So now I'll have to explain what I mean by exercise in just a minute. What are the degrees? And number of variables, that sort of thing. Yeah, just very basic. What do you, the structure of that system? Basic structure of that system, I mean. Okay, I like to think of exercises. When I'm trying to get up to speed, learn some things, I like problems to work on. I don't want to work on an open problem immediately. And my way of inviting you to learn about this is to think about exercises. Okay, I don't care if you do or not. I'm not going to come knock on your door on Pingree, ask for an exercise sheet. So this is simply an invitation to just think about these things. Okay. And let me be very clear. You're all welcome to talk to me. If you want to talk about solutions, I may or may not have written one out. May or may not have references for you to look at if you want for examples. You feel to talk to me. Okay.
Can I ask a question? So
yeah.
In the case of the K is algebraic because already this polynomial system gives us an algorithm.
Indeed. Yeah,
So-
like Gribner bases, for example.
For sure. So
Yeah.
I don't know. I'm not just familiar with. Is there an algorithm to decide if a polynomial system has a solution over a non-algebraically closed field, just in general, or if there's
I don't know.
or is
Well,
that?
I mean, even over those complex numbers, you're not getting any precision there, right? There's a lot of
Indeed.
assumptions you have to make on the field, K, to make the field computational. Then you're adding X number of variables.
Well, this polynomial system will be defined over the just the subfield that the entries of the T are contained in. So like we can, if they're over the rationals or something, then
You get some pretty crazy polynomials out of this.
They're going to have
Overlay.
I-
you can check whether they have solutions for this problem.
Okay.
In theory, not in practice.
I think, well, what if we consider the case where we're concerned about isomorphisms over the complex numbers, but maybe the T is really defined using some reasonable
In
substrate?
theory, this tensor answer. In practice, it does not, because Galway basis is not computable. That's correct.
Well, they're computable, but I'm just,
Okay.
they're just as good as the first algorithm, the first report search. They're better than the first one. So I'm just curious if we're thinking about, is it a decidable problem, you know?
Over the rationals, I think you can do that. I'm not sure how general you want your field to be. Maybe a field of fractions or something like that might work too. But I think in general,
The reference is probably decidable.
it's probably over the rational society.
You think so?
No, I'm not sure. Wait.
Diophantine is unknown.
But not
You
integer.
can check
We're
whether
not
the
saying
components are
integer
defined over the
isomorphism.
rational.
Sure, but over Q, Diophantine is, I think, unknown.
Oh, wow, then yeah.
Over Z, this is an interesting, I'm not entirely
Okay,
sure.
we don't know, but it sounds like people will have a nice beer.
Yeah.
Explaining it to each other. And
So an
saying-
interesting, so one question I have is if you take K to be the ring of integers, just Z, is that polynomial system always a decidable algorithm? It's not obvious to me, but nevertheless. Anyways,
I mean, is it automatic that you're going to get invertible solutions if you do this? You'd have to throw in some not equal to zero determinant conditions.
yeah, you should throw in more
So it might be an open
polynomials.
condition.
You can always.
You can add a variable and make it closed.
Okay.
Take your determinant, multiply by a variable,
Right,
set it
so
to
there's hope of doing something that you would never actually do. Got
You at least have a polynomial system.
Yeah.
You really do have that.
And you know, how bad is that? How big is that system? Is sort of what I'm asking, and you come to the conclusion that James has erred. Is just not gonna, and Martin as well, is not gonna do it this way for significantly large things. Okay, that's to say that the field K plays an important role in isomorphism, in determining whether or not two tensors are isomorphic. And, well, generally, with computational algebra, we're never given the objects in exactly the way we want. So, generally speaking, in general, the field, K, is not the field we want. And this gets to centroids, which Pete helped us understand. And I will go ahead and think, write up a little bit of what I mean by centroids here, which is of course the same as Pete's, but in case you need a reminder, the centroid, so let me just recall, yeah, we have V1, VL, V naught, that's my K tensor. The centroid, I noticed Pete was writing cen, so I'll do the same. Sometimes I write cent. You'll forgive me, I hope. A bunch of matrices in a bunch of endomorphism rings. Okay, that satisfies, well, many equations. I won't write them all out, but I'll say the following. For each j, you have v1, vj minus 1, x, j, vj, vj plus 1, and here's where some notational choices can be used to our advantage. I won't say more. X naught t, v. By v, I mean the collection of v1 through vl. And of course, I'm running through all possible v1, vl's in the various spaces. Capital V1, VL. Okay. So this is the high valence version of what Pete said just an hour ago. And of course, what he said was he was working with bilinear maps just with choice, and you of course generalize it to multilinear in the usual way. Okay. So exercise, and Pete mentioned this exercise, so I'm going to reiterate, but I'm going to do it in a few steps. Sen T is a K algebra. I do it a little bit step by step. What I mean it has a product. Given by, I'll just write the one particular coordinate, the usual product in my endomorphism ring. Yeah, composition if you like, matrix multiplication if you want in terms of matrices. Okay, show that it's a K algebra. It's closed under this product. Okay, if you do this, I think your proof will show that you could actually take an opposite endomorphism ring. You could flip the order of things. Your proof will very likely apply to just sort of randomly taking opposite things. That is to say, you just switch the order of multiplication. So basically, just use this proof, and you basically can conclude that oh no, no, I don't want to just say that. Don't want to say that just yet. No, what I said was a little bit wrong. Let me take that away. I need to say one more thing.
They'll figure it out.
Yeah, fine. But I want to have an assumption. I want to make this assumption very clear. If T is fully non-degenerate, not sure if fully non-degenerate was defined. I may have been asleep.
So you were asleep?
Pete defined it while you were sleeping.
In the front row. Indeed. Yeah, if T is fully non-degenerate, then what I wrote was correct. Then sen is commutative. Okay, I mentioned this and I want to make it very explicit, is because you actually have to use that. It's not necessarily true when it's not fully non-degenerate. So, fun exercise would be come up with one that isn't fully non-degenerate and show that it's not commutative.
Zero.
Yeah, that works. That'll work. Make your dimensions larger than 1. You've got yourself your example. Okay, so time. Good. Each VI is a sen T module. under the following action or product. X I'm thinking of as the x naught through xl times little vi is nothing more than, well, what could possibly act on this one? It's the only endomorphism that is assigned to act on this vector. You just take that one particular matrix or that one particular endomorphism, xi, acting on a vi. Okay, this turns each of the vi's into a SMT module. And what I want to do is I want to assume for the rest of the talk sen T is a proper field extension. Okay. I've been dealing with finite dimensional vector spaces. Sen is a finite dimensional algebra, and so this is then a finite field extension, an extension of finite degree. Pose these as questions. How? Oh, and I want a name for this. Let me use L, since I'm assuming it's a field. It's not always a field. As we saw in Pete's example, it can split. Okay, you can have a direct sum of two fields, for example. In this case, I want that field extension. How can we write a tensor TL, so that in just a minute, a L tensor? What I mean by that is it's L linear, not only just K linear, but L linear from T. Okay? And I want to think of each of these VIs as now L vector spaces. Okay? We've already seen an example of this. This is brilliant. I'm very happy that Pete demonstrated this for us on a very non-trivial example. So that's one question. Second question, how does this help? I invite you to think about the first question on your own. As Pete alluded to, it's kind of tricky. It seems obvious, and then when you put maybe finger to keyboard, it gets hard. A lot of bookkeeping, that's sort of what I mean.
Would it be okay if L was only contained in the centroid? Could you still do the same game?
Yes.
Okay.
Yes. And in fact, I believe that algorithm, that code that Pete demonstrated, will do just that. Sometimes it won't. Yeah. So I invite you to try this for yourself. If you'd like a reference, I didn't want to throw it on the slides. You can go to archive. I mean, you can ask me, but I'll mention it in case you don't want to talk at the moment. You just want to see this. You can go to archive. You could search my name and then Mima Stenczykowski right up here. There's a unique paper on the archive with these two authors, so you won't have any problems finding that. It's example 513. We do this very explicitly. So, and it's also non-trivial in the sense that it's kind of the same dimensions as Pete there. Okay. I wanted to cover a few more things, but I won't cover all those details. Yeah, if you want to learn more about how to actually do this, do talk to me. But maybe I'll just quickly get to the punchline. How does this help? Well, it's a sort of a dimensionality thing. I might have some very large tensor, T, and I might think of these as vector spaces. Let's just use A, B, and C. Right? And if L is an E, a degree E extension over K, then I know that A, B, and C are all divisible by E, and I can write a new tensor, T sub L, that is significantly smaller. A over E, B over E, and C over E. And if you just think of the brute force algorithm, you want to decide isomorphism, you get a huge amount of savings even for just a quadratic extension of your tensor. So factor 8, so to speak.
However, right, the entries are in a big field, not in a small field.
Indeed, yeah.
So, okay.
Yeah, you pay a little bit of extra cost, but it's not, you do get some savings. But indeed, yes. And that's sort of one way the centroid helps us with isomorphism. And I'll leave it at that. Thank you very much.